Effects of 4 drying methods on the quality of osmotically dehydrated cranberries. C. Baudry, G.S.V. Roghaven, C. Ratti, and T.J. Rennie. Department of Agriculture and Biosystems Engineering, McDonald Campus of McGill University. St. Anne de Bellevue, QC, Canada. Abstract. Partially dehydrated cranberries, osmotically dehydrated, were dried to low water contents using one of the following 4 methods: hot air drying, microwave-assisted convective drying, freeze drying, and vacuum drying. Quality evaluation was performed on all samples, including sensory evaluation, appearance and taste, texture, color, water activity, and rehydration ratio. Hot air drying produced dried cranberries with the best visual appearance, while freeze-dried cranberries had the highest rehydration ratio. The other methods presented similar rehydration ratios. There was no significant difference in color, measurements, and water activity. Few differences in texture were found except for freeze-dried cranberries, which had a lower toughness compared to the other drying methods, including commercially available dried cranberries. Microwave-assisted to hot air drying ratios increased as the moisture content decreased. Introduction. Several types of drying methods are commercially implemented for fruits and vegetables. However, all drying processes can be grouped into 3 basic types: sun and solar drying, atmospheric drying, including cabinet, tunnel, fluidized bed spray, and microwave dryers, and subatmospheric drying. This study deals with 2 different atmospheric drying methods, microwave-assisted convection drying and hot air drying, along with 2 subatmospheric drying methods, freeze drying and vacuum drying. Over the last few decades, it has been recognized that microwave heating can lead to potential economic, engineering, and social benefits. Radio frequency, RF, and microwave, MW, are forms of electromagnetic energies that are used in industrial applications such as drying of foodstuffs, wood, papers, and textile. Radio frequency and microwave have a penetrating effect on the product, which causes volumetric heating. Materials that are absorbers and transmitters of microwaves are said to be dielectric, and when subjugated to microwaves, heat is generated through the materials. An advantage of using microwave technology is the possibility of combining diverse drying methods with microwaves. For example, the combination of convection hot air drying with microwaves has been adopted for several food processing facilities in order to reduce drying time and improve food quality. In their comparison of 4 drying methods on the quality of low-brush blueberries, Yang and Atala determined that the samples dried using a combination of hot air and microwaves had a higher sodium retention than samples dried under other methods and a lighter color than freeze-dried and vacuum-dried samples. Venkatachalapathy and Raghaven determined that osmotically partially dehydrated blueberries, dried afterward by a combination of hot air and microwaves, resulted in a final product quality comparable to freeze-dried samples, but in a shorter drying time. In addition to their possible combination with hot air, microwaves can also be combined with freeze-drying or vacuum drying in order to dry food materials. Cohen et al. Reported that the combination of microwaves with freeze-drying significantly increased the drying rates of peas and enabled the rehydration capacity of the dried product. Microwave vacuum dryers are in commercial use for the production of fruit juice concentrates, tea powder, and enzymes. Yang Sawadagal and Gunasekharan studied the combination of microwaves and vacuum in order to dry osmotically dehydrated cranberries. They found the storage stability of the resulting product comparable to that of cranberries dried by conventional methods. Fruit and vegetables can be dried using hot air as the drying medium, which is often found as the simplest and most economical method. In hot air drying, convection is the main mode of heat transfer. In this type of system, 4 main factors can affect the rate and total time of drying: the physical properties of the food, particle size and geometry, the physical arrangement of the food with air and physical properties of the air, temperature, humidity, velocity, and the design characteristics of the drying equipment. The main disadvantages of hot air drying are the non-uniformity obtained in the dried sample, the slower drying rates compared to other drying methods, and the quality of the resulting product, which may be improved by using other drying methods. Research has determined that the taste, color, and overall quality of dried berries can be improved by using alternative methods, such as a combination of hot air and microwaves. Freeze drying has been used for a wide variety of products and is a commonly used drying method for high-value products. Although it has disadvantages, such as expensive equipment and the need for special packaging to avoid oxidation and moisture pickup, freeze-drying can be justified in some situations since the nature of freeze-dried product is already altered. An important feature of freeze-drying is the structural rigidity of the frozen product, which can prevent the collapse of the solid matrix, resulting in freeze-dried products that tend to have a porous and non-shrunken structure with an excellent rehydration capacity. When examining 4 different drying methods on low-brush blueberries, Yang and Adala determined that vitamin C retention was higher in freeze-dried berries compared to samples dried under forced air, vacuum oven, and microwave convection. Furthermore, it was determined that freeze-dried along with vacuum-dried blueberries had higher soluble fluid retention and were darker and redder than forced air or microwave convection dried berries. Of the 4 methods, freeze-drying was found to produce dried berries with the highest rehydration ratio and the lowest bulk density. Zani and Ramaswamy performed a quality evaluation on osmo-convection dried blueberries. The results from this drying method were compared to those of freeze-dried blueberries. The results obtained were similar to those of Yang and Atala, where the rehydration ratio was higher for the freeze-dried samples than for the osmo-convection dried samples. The main limitation of using freeze-drying for fruits and vegetables are its high investment and operating cost. Gabrowski et al. Reported that when drying cranberries, freeze-drying had the lowest energy efficiency compared to drying by vacuum and various air dryers. Atmospheric freeze-drying is one alternative to reduce the cost of the process, where simple equipment such as convection fluidized bed can be used. It was reported that several foods, including mushrooms and carrots, were dried under atmospheric freeze-drying, achieving improved heat and mass transfer and shorter drying time compared to vacuum drying. Vacuum drying presents various advantages, mainly offering a product temperature lower than conventional drying methods and preventing contact with air, which can reduce oxidation of the product. Vacuum drying has been applied to the dehydration of citrus juices, apple flakes, and various heat-sensitive products in which the ascorbic acid retention is important. This method is also used for the extraction and concentration of essences and flavors. Even though the degree of vacuum and the temperature for drying depend on the sensitivity of the product, most vacuum applications use levels of absolute pressure of 7 kPa, at which the boiling point of water is reduced to 39 C. Since vacuum drying is an expensive technique, it is often used as a secondary dryer. Moisture content of high moisture food can be reduced to 20 to 25% by a conventional, less expensive method, and then vacuum is applied to bring the moisture down to the desired level. The selection of the proper drying technology can affect the final product quality and the drying economics. The purpose of this work is to further the study of finished drying of osmotically dehydrated cranberries using different drying methods with the aim to increase the knowledge base for the drying of this fruit. Objectives. The objectives of this study were to compare the characteristics of osmotically dehydrated cranberries, finished dried using 4 different methods: microwave-assisted convection drying, conventional hot air drying, freeze drying, and vacuum drying, and to perform a quality evaluation on the dried samples. Materials and methods. All tests were performed on cranberries, Vaccinium macrocaprum of the Stevens cultivar. The fresh fruits were frozen after harvest and thawed by immersion in ambient temperature water for 1 hour just prior to osmotic dehydration. The fruits were initially cut in half and osmotically dehydrated by placing the fruits in high fructose corn syrup 76-degree bricks at 1:1 fruit-to-sugar ratio at ambient temperature 23 C and for 24 hours. The fruits were then rinsed with warm tap water to remove excess syrup and then gently surface dried with absorbent towels. Samples to be freeze-dried were frozen to a temperature around -40 C until they were used for finished drying. The samples to be finished dried by the remaining 3 methods were refrigerated at 2 ± 1 degree Celsius. The mean moisture content of the osmotically dehydrated cranberries was 57 ± 1% wet basis before finished drying. The mean initial moisture content of fresh, thawed cranberries was 88 ± 1% wet basis. Microwave-assisted convection drying. Combined hot air and microwave drying tests were performed using a custom-designed laboratory-scale convection and microwave dryer. The microwave cavity had dimensions of 40 by 30 by 25 centimeters. The dryer was equipped with a 750-watt, 2,450 MHz microwave generator that was connected to the multimodal cavity via waveguides. Power meters were provided on the top of the waveguides assembly to monitor incident and the reflected power. Incident power was constant and set based on a 0.75 watt per gram power density and on the initial mass of the samples, 125 grams. Microwaves were generated for a cycling period of 30 seconds on, 60 seconds off. Reflected power was manually maintained close to zero throughout the experiments by the use of 3 tuning screws inserted in the top of the waveguide assembly. Heated air was continually blown through the samples, placed on a single layer on the sample holder by a 0.25 kilowatt blower placed underneath the drying cavity. A metal grate on the bottom of the cavity was used for the inlet air, and the metal grate on the side of the cavity was used as the outlet. 3 2-kilowatt electrical heaters were used to heat the air. The temperature and velocity of the air were maintained constant throughout the tests, set at 62 plus or minus 1 degree Celsius and 1.0 plus or minus 0.1 meters per second, respectively. The sample holder was equipped with a strain gauge so the mass of the samples could be monitored throughout the drying process. The cranberries were spread on a single layer on the holder. Temperatures of the inlet and outlet air was measured by the Type T thermocouples, and the temperature of the sample was measured through a digital fiber optic thermometer embedded into a cranberry. Nortec Fibronic Inc., Canada. Temperature, plus or minus 1C, and mass resolution of 0.01 grams. Data were recorded by the Data Acquisition System. HP 34970A-Data Acquisition Switch Unit, Hewlett-Packard, USA. A computer program was written on HPVEE to monitor the drying process. A schematic of the system can be found in Venkatachalapathy in Raghaven. The sample was removed when it reached a moisture content of 15% wet basis and refrigerated at 4 plus or minus 1 degrees Celsius until quality evaluation was performed 1 week later. Hot air convection drying. The tests were performed using the same laboratory scale dryer as used with the microwave-assisted drying. The microwave generator was turned off for all hot air drying tests, and the blower and heaters were at the same setting as the microwave-assisted drying. The inlet air temperature and flow rate were the same as in the microwave-assisted drying tests. All temperatures and mass data were recorded as above. The sample placed on a single layer of fruits on the sample holder was removed from the dryer once it reached a moisture content of 15% wet basis. It was refrigerated at 4 plus or minus 1 degrees Celsius until quality evaluation was performed 1 week later. Freeze drying. The tests were performed using a laboratory scale freeze dryer. The freeze dryer, Unitop 400L Virtus USA, was equipped with 12 600 milliliter bottles linked to the main oven cavity where vacuum was applied. A manual valve connected each bottle to the oven cavity, hence the bottles could be removed individually while in operation in order to monitor the mass of each sample. Another advantage of using these bottles was the ability to perform drying at room temperature. The mass of the samples, initially 25 grams, was measured periodically every 2 hours using a digital balance giving precision up to plus or minus 0.01 grams. The sample was removed once it reached the moisture content of 15% wet basis and refrigerated at 4 plus or minus 1 degree Celsius until quality evaluation was performed 1 week later. The applied vacuum during the freeze drying experiment ranged between 0 and 1.3 PA at any time. The condenser temperature was set at negative 85 degrees C during all tests, and the ice formed on the condenser was removed through the defrost cycle, done following every second experiment. The vacuum pump operating the freeze dryer reduced the pressure from normal atmosphere to 2.7 PA in approximately 20 minutes. Vacuum drying. The tests were performed using a laboratory-scale vacuum dryer. The dryer was a VWR Scientific Model, Johnson Scientific Inc., Canada. The vacuum pump was operated with a one-phase 0.186 kilowatt, 0.25 horsepower, 115-volt electric motor. The tests were performed on a plate temperature inside the vacuum oven of 70 degrees Celsius and a pressure of approximately 7 kPa. A vacuum of 94.6 kPa. The mass of the sample, initially 25 grams, was measured periodically, every 2 hours, by breaking vacuum and stopping the experiment just long enough to measure the mass of the sample. A digital balance was used to measure the mass to a precision of plus or minus 0.01 grams. The sample was removed from the dryer when it reached the moisture content of 15% wet basis and refrigerated at 4 plus or minus 1% C, until quality evaluation was performed 1 week later. The vacuum pump operating the vacuum dryer reduced the pressure from atmospheric to 7 kPa in approximately 2 minutes. The moisture released from the product was captured by Dry-Rite, anhydrous calcium sulfate, which was replaced when saturated. Quality evaluation. In this works, 5 methods were selected for evaluating the quality of dried cranberries. A sensory evaluation of the sample was performed along with the measurement of surface color, texture, water activity, and rehydration capacity. Sensory evaluation of a product, though subjective, is an important part of quality evaluation since it represents the same procedure that would be used by a consumer. The scale that was used for the sensory evaluation of the dried cranberries is shown in Table 1. The main drawback of this method is the subjectivity of the judges involved. Due to the high number of samples evaluated, there was difficulty in having the same judges for all tests. This would have led to data applicable for statistical analysis, where the judges would have represented a block in a randomized, complete block design. However, because the judges differed from test to test, the data obtained were not valid for statistical analysis, but were still considered important since they gave an idea of the consumer's reaction to the different samples. Judges were asked to evaluate the overall appearance of the sample, along with its taste. Objective measurements, including water activity, rehydration capacity, surface color, and texture, were determined. The water activity of the dried cranberries was measured using a water activity meter Model 3 TE Series Meyer Service and Supply, Ontario, Canada. All measurements were performed at 40 degrees Celsius, and the water activity meter was calibrated before each series of tests. The sample was manually sliced and placed into the 40 mm diameter sample cup as fast as possible to avoid moisture loss or pickup. The sample was a single layer of sliced pieces covering the bottom of the sample cup. The rehydration capacity of a dried product is also an important factor to consider. Rehydration ratio is the ratio of mass of the dehydrated sample to the mass of the rehydrated sample. It is useful to determine how the dried product will react to future contact with moisture. For example, dried fruits used in breakfast cereals should have some rehydration capacity in order to absorb moisture from the added milk. In this work, rehydration capacity was determined by placing 2.5 plus or minus 0.05 grams sample in boiling water for 4 minutes. The sample was then transferred to a 7.5 centimeter Buchner funnel with a Whitman No. 1 filter paper. Water was drained out by applying a gentle suction until no more drops were observed. The sample was then removed and weighed, and the rehydration ratio was calculated. 2 samples were used for each drying trial. The color of any dried product is an important factor to consider, as it is one of the main attributes to evaluate quality. The color of dried cranberries is caused by red anthocyanins and yellow flavonoids. The surface color of the samples was measured using a chronometer, model CR-300X, Minolta Camera Company Limited, Japan, equipped with a measuring area of 5 mm diameter, which provides values for the 3 coordinates, lightness, L, redness, A, and yellowness, B. The reading was done on the external side of the cut cranberries, and the mean of the 3 readings at the same location was taken. 5 different fruits from the same sample were randomly tested. Mean color values of cranberries dried under different treatments were compared to those of fresh, frozen thawed cranberries, which were considered as a reference. Commercially available dried cranberries were not used as a reference for color because of the unknown processing conditions. The data obtained were converted to hue angle, H degree, and chroma, C asterisk, an index somewhat analogous to color saturation or intensity. Color difference, delta E, was also calculated in order to evaluate the change in color between fresh, frozen thawed, and the dried cranberries. The equations used for the conversion can be found in McGuire and Yangaswadigal and Gunsakaran. The textural characteristics of the dried cranberries were determined by using Instron Universal Testing Machine, Series 9 Automated Materials Testing Systems 1.16. Compression tests using a Kramer shear press were performed on 15-gram samples for the osmotically dehydrated samples and 4-gram samples for the controls. These masses were used in order to have a single layer of dried fruits in the 66mm by 66mm Kramer shear press cavity. A 50 kilonewton load cell was used at the crosshead speed for all tests was 160 millimeters per minute. 3 samples were tested from each batch. Different parameters were obtained, including Young's modulus and toughness of the tested samples. Experimental design. All experiments were conducted on triplicate, and the data were subjected to analysis of variance, ANOVA. Differences were identified as significant or non-significant based on Duncan's multiple range tests for each variable, i.e. drying methods. A significance level of 0.05 was used in all cases. Results and discussions. Drying characteristics. Osmotically dehydrated samples were microwave-assisted dried, hot air dried, freeze-dried, and vacuum dried to a final moisture content of 15% wet basis in 3.5, 12.6, 5.7, and 4.6 hours respectively. All these times were found to be significantly different based on Duncan groupings. Figure 1 presents the drying curves for each situation where the mean of the 3 replications is plotted. Drying rates were calculated by dividing the change in moisture, kg of moisture, between 2 measurements by the time between the 2 measurements and the initial total mass. From Figure 2, it can be observed that the constant rate drying period is not present. It should be noted that because different times between measurements were used, it appears the different drying methods start off at different moisture content, which is not the case. This is similar to the results of Lewicki and Leonard, where no consistent drying rate period was found during drying of osmotically dehydrated apples. This phenomenon was explained by the fact that the water content of the investigated material after osmotic dehydration fell below the critical water content. Other authors, such as Barbanti et al., observed that there was no constant drying rate period between the air drying kinetics of the fruit following the osmotic dehydration. Grabowski et al. Studied the drying kinetics of raw cranberries and sucrose-infused cranberries and showed that the sucrose-infused cranberries had no constant drying rate period and that the sucrose-infused cranberries had, for the most part, a lower drying rate than raw cranberries at the same moisture content. The drying rates shown in Figure 2 are not based on a constant evaporating surface, as there was shrinkage during the drying process. However, the shrinkage was not measured and is not reported in this work. Figure 3 shows an interesting comparison between microwave-assisted and convective drying rates. Both experiments were run in the same equipment and under identical process conditions, but for the addition of microwaves. In this figure, the ratio of microwave-assisted to convection drying rates is plotted against moisture content, wet basis. It can be seen that at high water contents, microwave-assisted drying rates is approximately 3.5 times higher than the convective drying rate. However, when water content drops below 0.4 kilograms water per kilogram dry matter, the ratio of drying rates increases dramatically as moisture content decreases. As moisture content of the material decreases, internal heat and mass transfer control the convective drying process. Microwave-assisted drying will, in one hand, supply the necessary heat to reduce the internal heat resistance. Figure 4 presents the internal temperature of the cranberries during microwave-assisted and hot air drying, showing a 10% difference in product temperature throughout the process. In this particular study, the microwave power density was based on the internal mass of the cranberry. As the cranberry dried, the power density increases, though the total power remained the same. On the other hand, the internal pressure built up during microwave-assisted drying would help to create a porous structure, reducing the internal resistance to mass transfer and enhancing the drying rate with respect to traditional convection drying at low water contents. Sensory evaluation. Even though the data from the sensory evaluation is not statistically valid, it still shows the appreciation of the judges for all samples based on both overall appearance and taste. Conventional hot air drying seems to have a slight advantage over the other methods based on overall appearance of the dried samples. This is probably due to the uniformity of the sample. For example, cranberries dried with microwaves produces a few darker fruits, and a few fruits dried under vacuum were less aesthetic, probably due to excessive bleeding of the fruits during drying. Data obtained based on the taste of the samples seems to present no difference among the different drying methods. The water activity of all dried samples was measured at 40 degrees Celsius and was found to be lower than 0.7, which is often referred to as the limit for intermediate moisture foods. In fact, foods having a water activity between 0.4 and 0.65 are considered as dried products, whereas those having a water activity between 0.65 and 0.75 represent intermediate moisture foods. Referring to Table 2, no significant difference is observed for the 4 drying methods. This was expected since water activity is closely related to moisture content of a product, and all samples were dried to the same moisture content. The important feature to consider is that all values of water activity are below 0.7, which indicates that the growth of molds, bacteria, and yeast is not promoted and enzymatic reactions are not likely to occur. In this work, the measurement of water activity was considered for determining the stability of the samples, not for measuring differences between treatments. Rehydration ratio. As observed in Table 2, the rehydration ratio of freeze-dried cranberries was significantly greater than that of the fruits dried under other methods, as expected. In fact, freeze-drying has been shown to produce samples with greater rehydration capacity than other drying methods, because the internal structure of the fruit remains quite undisturbed. This is due to the structural rigidity of the frozen product, which can prevent the collapse of the solid matrix remaining after drying. Therefore, freeze-dried products tended to have a porous and non-shrunken structure with an excellent rehydration capacity. Lewicki and Pollock observed that there was no shrinkage and large voids were formed in freeze-dried apples. They also found that during convective drying, shrinkage stresses caused numerous breaks in cell walls, resulting in many small cavities but very few large voids. During rehydration, the large voids would most likely help increase the rehydration capacity of the fruits. Vacuum drying produced samples with the second best rehydration capacity, along with convective drying. However, samples conventionally dried had a convection ratio that was not significantly different from the lowest value observed with the microwave-assisted samples. Similar results were observed by Yang and Atala when drying blueberries. In fact, the authors determined that blueberries dried using microwave-assisted drying had the lowest rehydration capacity compared to fruits dried under freeze-drying, vacuum drying, or convection. Color characteristics. Mean color values of cranberries dried under different treatments were compared to those of fresh, frozen thawed cranberries, which were used as a standard. The data obtained of lightness, redness, and yellowness, along with the calculated hue angle and chroma and color difference, are shown in Table 3. No significant difference was observed in the values of hue angle, chroma index, and total color difference. It would be expected that cranberries subjected to higher temperatures would have lower values of redness due to the degradation of anthocyanin pigments, which are closely related to the redness of fruits. Anthocyanins are reported as not being chemically stable, and their exposure to heat treatments can enhance their oxidation, thus resulting in the degradation of color. However, no such color difference is observed between cranberries subject to higher temperatures in microwave-assisted drying and those freeze-dried or vacuum-dried. Also, by looking at total color difference from the 4 drying methods, one would expect significant differences between cranberries dried under microwave-assisted drying compared to those of other methods. However, no such difference was detected based on Duncan groupings. This is probably due to marked variations within the values, which was not shown when looking at the means. Textural characteristics. Toughness and Young's modulus were used to describe the texture of dried samples. These values are shown in Table 4 and were compared with the toughness and Young's modulus of commercially available dried cranberries. Significant differences among treatments were not observed for Young's modulus, whereas some significant differences were observed for toughness values. The toughness value closest to that of commercially available product is seen with cranberries dried with microwaves. Freeze-dried cranberries had the lowest toughness compared to the other samples. Both vacuum-dried and hot air-dried fruits had values of toughness higher than freeze-dried samples and lower than microwave-dried samples. Possible causes of higher toughness include exposure to high heat along with the presence of certain pre-treatments such as osmotic dehydration. Conclusions. Finishing drying of osmotically dehydrated cranberries by 2 atmospheric and 2 subatmospheric methods were investigated in this study. A significant difference was observed in drying times, where the shortest time was obtained using microwave-assisted drying. The longest drying time was observed for hot air drying alone, with a mean value of 12.6 hours to dry cranberries to 15% wet basis. The sensory evaluation performed by judges determined that all 4 drying methods led to product with acceptable taste and overall appearance, and the samples dried using hot air presented a higher uniformity in appearance. All values of water activity were found to be lower than 0.7, which indicates microbiological stability of the end product. Important differences were observed in the rehydration ratio of the dried cranberries, with freeze-dried cranberries having a rehydration ratio greater than cranberries dried under other conditions. No significant difference was observed in surface color and Young's modulus among the 4 drying methods. However, significant differences were observed in the toughness of the samples, where those dried using microwaves had the value closest to that of commercially dried cranberries, Craisins, trademark Ocean Spray. Freeze-dried cranberries had the lowest value of toughness and would therefore be less appreciated by consumers. Overall, the results from this work indicate that 4 drying methods can be applied to dry osmotically dehydrated cranberries. However, specific characteristics show that some methods may be more appropriate than others for this specific product. For example, the toughness characteristic of the dried fruits indicate that the use of microwaves to dry cranberries resulted in a product with a similar texture to commercial craisins. The application of microwaves significantly increased the rate of drying compared to conventional drying, especially at lower moisture content. However, the rehydration characteristics of cranberries dried with microwaves were lower and could be improved by lowering the maximum internal temperature of the fruits being dried. Future studies should include more tests using microwave, since this alternative seems to be appropriate to dry small fruits such as cranberries. A method to maintain the internal temperature of the fruits as low as possible during microwave drying should be examined, and an applied vacuum could achieve this objective.